ideas grow, we're going to need some better ways for managing them. So I like to say anything worth doing is worth doing 100 times. That's a bit of a joke, but it's true that computers are very good at doing things repetitively, but when you're talking about programming maths, even putting together manually 3 of something can easily exceed my patience to knit together patch tables. My computer science background trained me to always be on the lookout for a way to do something like that in the general case. If you can handle 1 of something and you can handle 2 of something, don't just like keep making more and more copies to get to 50. Think of a way of handling all 50 all at once. Computers are very good at repeating and looping. We should let them do their job. Now we're going to learn some additional mechanisms that give us these powers, and the cost is that the added potential can make things confusing, especially if used illogically. So I'm going to try to talk about how to use these more powerful mechanisms in a way that keeps you out of trouble, that makes your program still make sense even as it's getting more and more powerful. So what are we going to learn in this session? Well, some deep knowledge and some shallow knowledge, as I like to divide things. So the deep knowledge, we're going to get the beginnings of an intellectual toolbox for breaking down larger problems into smaller problems that you know how to solve and test. We're going to get greater power to multiply your ideas from 1 to many. And on the deep side, we're going to sort of learn this approach to the world, this habit of this inclination of being on the lookout for general case solutions. The idea that like don't do something 3 times, do it n times. At the same time, I think this is also on the deep side. I think there's a very human tendency to get distracted from creating art and engineer a really cool system. So you know, you might want to ask yourself, is it really worth the investment of doing this the really sort of programmery right way? Maybe you should just make something quick and dirty and messy that gets you to your artistic goals and then just kind of forget about it. So you need to be very careful in balancing your time and energy of doing something in the best engineered possible way versus just kind of quick and dirty, get the job done and go on to thinking about other stuff. Lastly, on the deep side, we're going to talk about top-down versus bottom-up development styles, 2 different approaches to solving larger problems. On the shallow knowledge side, we're going to learn all about the mechanics of Max's subpatcher and encapsulation mechanisms. That'll be the main way that we start dealing with trying to tame complexity in this session. And we're going to also talk some shallow knowledge. We're going to teach how to get a wub bass sound. So let's dig right into our wub bass synthesizer. So I got a couple of examples that I previously made. So I found this website online. There's a little tutorial of how to get a wub bass sound. There's a link here you can click. So it's got a frequency, in this case set to 110 hertz, and it's a 3 oscillator type situation. So we've got a sine wave, a cycle tilde object at that frequency. We've got a square wave, that's what Rex tilde gives you, and it's an octave down but then detuned. So it's down an octave but 12 cents back up. So that's what this 0.5035 frequency ratio is giving. And then the third oscillator is a triangle wave that is a fifth up but 24 cents down. So these are just some magic numbers. These intervals and these detuned amounts again that I just got from this one particular tutorial online. You can and will modify these to your own taste, but that's the idea. So if we turn this up. So we've got this sort of inharmonic out-of-tune chord that we're moving around and we're sort of transposing as we play notes on this keyboard. And let me also point out that we're computing the frequencies of all these oscillators using signals. So currently I'm using an object called sig tilde that takes an event, in this case a floating point number, the output of this M2F object, and makes a signal whose value sample by sample is just that same thing until you move it. So if you look at the output of this, it's a step function where it's just a signal that's holding at some number for however long and then goes to another number, holds it that for however long. So here we go. This is our simplest first part, just the 3 oscillators with their frequency ratios. So let's look at number 2 here. So this part is all the same, but we're passing it through a little distortion. We're using the overdrive tilde object, and that's going to give us an even richer sound. We saw in the last lesson how adding distortion to a sound will give additional harmonic components. So we're doing that. And then we're also passing it through a resonant low pass filter, low res tilde. You'd think that would be a bit crusher or something that would reduce the resolution, but no, it's a low pass resonant filter. That's where that name comes from. And we're setting the frequency to 200 hertz, but we're going to use here. Let's just disconnect this for now, and we can hear that on its own. So there's a note. Make it a little louder, and we can overdrive it less or more. And we've got this filter that, if we increase this number, we're bringing more and more high frequency components in. So let me throw a spectroscope in so we can see what's happening. So the overdriven signal has a lot of high frequency components, and the filter is cutting. It's a low pass filter, so it's cutting out highs. But as we open the filter up, it's letting the highs back in. Sorry, I'm zoomed in, so it's giving this weird stuff as I go too far. So when it's down, it's very low, bassy sound with the highs cut. So that's a wow, wow, wow. That's what gives us that web bass sound is opening and closing that filter. And so we're going to do this automatically. We're going to use a sine wave, this cycle tilde object, which we're going to set to a low frequency like 2 hertz. And then we're going to scale the output. Normally, by default, a cycle goes between -1 and +1. But we're going to scale that to the range from 40 to 3000. And I'll talk in a moment about that last outlet. And so when we put the signal into the low res, we're opening and closing that filter regularly with this sine wave. So every 2 hertz, we're opening and closing it. And we can change the rate of that vibration. I think that might be a little bit too much distortion. Scale tilde can do a perfectly linear translation where it's going from -1. The input range maps to the output range. It can be totally linearly, but you can also do it on an exponential scale. So it's just basically changing the shape of this curve. Okay, so that's part 2. So again, we've got our same 3 oscillators. We're now putting them through a little bit of fuzz, and we're passing them through this low pass filter, and that's what's giving us this vowely wow, 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 wow sound, because we're opening and closing this filter using this low frequency oscillator, this cycle that we set to low. By the way, we could set this cycle as high as we want. There it is at 15 hertz. There it is at 118 hertz. Now it's so high that, so just because we're calling it a low frequency oscillator, it doesn't have to be low frequency, but to get the sort of classic web bass effect, you want to set it to something that's maybe from 1 to 10 hertz. Okay, so to get musically interesting results out of this synthesis, we're going to need a bass line. We're going to need to be able to compose a melody where it's playing a certain note and another note and another note and another note and so on. Maybe we'll be repeating. Maybe we want to synchronize it with some drums, and we want to also have this this wubbing sound, this the frequency of the oscillation change when the notes change. So it turns out there's a really fun object built into Max called techno tilde that is going to be a nice way to control this. Signal-driven step sequencer. So let's look at the help patch. So there's another object called JSUI. So this is a JavaScript-based interface that's designed to go with techno. So what happens here? Let's just turn this on. So this is a sequencer that is setting amplitude and frequency, pitch and amplitude for something. Doing this a little louder. We can make it so you can click on different parts of it. So here's the amplitudes. If I click, I'm moving the samples up and down. Here's the decay. And if you option click, you can change the frequency. Right, so these are all smoothly connected. So it's giving you pitch and amplitude as a function of time without any necessarily discrete notes. These are all just kind of sliding up and down. And one of the coolest things is that you can set the speed that you go through it at signal rate. So now we're going through the entire bass line 1.9 times a second, 6 times a second. In fact, we can go through it so fast that instead of being a bass line, it itself becomes a tone. So that's kind of fun. But it's designed to be used at these kind of slow speeds. Okay, so let's say we want to now connect this techno to our oscillators, our web bass thing that we made here. So things are getting messy, and that's the point. I'm trying to come up with an example where it just gets a little bit unmanageable here. So let's try taking our web bass here. Let's just do it the naive way that we've known all along. We'll copy that. We'll paste it into this help patch. We'll move it down here. We're running out of room in the help patch. Our screen isn't tall enough, but we're still gonna make it work here. We'll delete some of this stuff just so we have more room. Goodbye to you. Select all. Move it up. Let's turn this off while we're working. So our pitch is here. So we want to connect the pitch to our own pitch, which is right here. I guess I don't want a sig tilde. I think that's gonna be fine. So we'll get rid of all the old stuff that was making sound. We don't need this stuff for now. We don't need this stuff for now. So we'll Copy all this stuff, move it up a little bit more. What else are we gonna do? I'm not even sure what that is. We'll delete that. So here's our amplitude, and we'll make it control. We will scale it. So amplitude normally is between 0 and 1. So we'll forget about this cycle that we had, but we'll keep the scale, and we'll make it scale, expect an input signal that goes between 0 and 1 instead of -1 and 1, and we'll take it from here. And then we'll make it control that filter and also the actual amplitude. So we'll take our filtered sound and we'll multiply it by this same time varying amount that's coming out of our techno. Okay, so it doesn't sound very much like dubstep, but at least we connected it to our new thing. But here's my big point: we're running out of space on the screen. If we wanted to add more features to this, let's say we wanted to change what scale it uses, and we wanted to like paste in one of the patches that we used in the last session to compute scales. We're just running out of room. It's just gonna be too difficult to do it all in one patch. Now it's true, we could zoom out, and then we could have like a huge patch that like you need to be zoomed all the way out even to see the whole thing, and then you could scroll around and zoom in on different sections. But I don't think that's a good way to work. I'm gonna turn off sound here. I think it's good to be able to just look at the patch and see the whole thing there. And if there's more stuff in your patch than can fit on one screen, then that makes me think I need to encapsulate some of this. So that's exactly what this whole session is about: is subpatches and encapsulation. So instead of taking all this stuff and pasting it as is into the main patch, I'm going to do another version with a subpatcher. First of all, let me say, you can make it look better in presentation mode. So I made a presentation mode of this patch that hides everything and only shows the parameters that are most fun to play with. Here's where I have a start window here. Okay, so we're not looking at all of what makes the patch. We have this presentation mode that lets us just play with the parameters of it. But even so, at some point you're going to need to look at the whole patch. So if the patch takes up way more than one screen full, then you're going to have a hard time looking at it. So what I'm going to do is I'm going to select all, and I'm going to unselect these, because these are the parts that are outside the part that I'm thinking of. Okay, so I've got everything except the keyboard and the M2F and the gain and the DAC and the start window. Everything else is selected right now, and I'm going to say edit, encapsulate. And boom, look at that, it all went away, and it replaced it with this single thing that says P. So P is short for patcher, and this is an object that has a bunch of other objects inside it. So if I lock the patch and I double click on the patcher, then boom, look at that, it all went away, and it replaced it with this single thing, everything except the keyboard and the M2F and the gain and the DAC and the start window. Everything else is selected right now, and I'm going to say edit, encapsulate. And boom, look at that, it all went away, and it replaced it with this single thing that says P. So P is short for patcher, and this is an object that has a bunch of other objects inside it. So if I lock the patch and I double click on the patcher, then you see subpatch. And all this stuff that I encapsulated is now sitting in the subpatch. And I can, if I want to look inside, I can, and then when I close it, then I can just look at it. Now it doesn't need to be so wide, and it should have a name. So I'm going to call it wub. Okay, so this one thing, pwub, it takes in a frequency, and it outputs a signal, and we look at it. So it has one inlet and one outlet, because when I encapsulated it, there was one thing leading into all that mess that I encapsulated, and there was one thing leading out of that mess that I encapsulated. So it gave an inlet and an outlet to this patcher. And if you look inside, that right there is a max inlet. It's got a downward pointing arrow showing that it's something coming in, and it's number 1, because if you had multiple inlets, if I duplicate this, they would have different numbers. And likewise, there's an outlet down here, which has the same downward pointing arrow, but on the top here. So that's telling you that this is an outlet. And again, if I duplicated this, if I made multiple outlets, then they would be numbered sequentially. Notice that when I made those extra inlets and outlets inside the subpatcher, that the external view of the patcher got the second and third inlet and second and third outlet. And it all updates dynamically. So if I delete this third inlet, boom, it happened here, and I'll do it again. I'll delete the second inlet, keep your eyes over there. It's gone. So these inlets don't do much. Now, I'm having second thoughts about exactly the way that I did the encapsulation, because I think I want to make the control of the cutoff frequency also be something that's accessible to the outside world. So this is one of the biggest deep ideas of encapsulation. The idea that there's some details that are inside the subpatcher that are encapsulated, like what is the setting of the overdrive, what are the exact ratios of frequencies for these 3 oscillators, what are the spectra before and after we use the filter. So this is all the stuff that's internal to the logic of wub. And to the outside world, if you're just a user of wub rather than the person that's writing wub or seeing how it was written, then all you need to know is you send it a single frequency and it makes that note and it comes out. But now I'm changing my mind. I'm thinking I want to make it so that this filter cutoff is also something that's accessible from the outside world. So I can de-encapsulate it. I can change my mind. I'm going to make a little bit more physical room in the patch. I'm going to select that. I'm going to say edit, de-encapsulate. And it just got rid of my patcher. In fact, it made the window go away. And it put it back there. And now I'm going to unselect all of this stuff, the stuff that is my low frequency oscillator that's changing it. And I'm going to re-encapsulate. And now you see that there's a second inlet to my patcher, which I'm again going to call wub. And so basically I just made a conceptual decision that the implementation of the cutoff frequency, the part that is a filter that controls the signal, and the idea that I'm going to look at the spectrum before and after, that's all still inside the wub. That's part of the insides of the object. That's part of the implementation of this idea, which when you close it, you're allowed to not think about that. You're allowed to just say, well, cycle tilde is a box that has a certain behavior. I put a number in, a sine wave comes out. Scale tilde is an object that has a certain behavior. I put stuff in and stuff comes out. And now wub is just an object with a certain behavior. I put stuff in and stuff comes out. I don't want to underemphasize this point because it's one of the key aspects of programming in Max is that you get to decide what the boxes mean. You're given a whole large collection. We've said it's about 600 objects that are built into Max, and you can do quite a lot just by wiring those objects together. But to really go crazy programming in Max, you need to make your own objects. And the first step towards doing that is just encapsulating stuff in subpatches like this. So now when I'm looking at the top level patch, I see, okay, well, there's some wub stuff. And if I want to just send it some values, I can. And if I want to go inside and see what it's doing, I can. So it gives me the choice of what to think about. It lets me get real nitpicky and low level and look inside the patcher and see exactly how it works. And also lets me get very high level and sort of trusting and saying, okay, well, I got a patch that does something, so I'm not going to worry about that anymore. I solved that problem. I achieved success. I made a wub synthesizer, and now instead of just staring at the details of how it's implemented all the time, I'm just going to put a box around it and just use it without thinking about what's happening inside. So this is encapsulation. So to be clear, this cycle tilde object is built into Max, and if I double click it, nothing happens. There's nothing inside. It's actually written in C, and it's distributed as compiled machine code for whatever platform you have, and it's a sort of indivisible object. There's nothing that you can do inside it. But this patcher does have stuff written inside, because although cycle tilde was written in C, and you can't access it directly from Max, likewise scale tilde, message boxes, the oscilloscope, M2F, all the things we're looking at, these are all built into Max, and you can't get inside them any further. They're indivisible. But patchers are written in Max. That's the whole point. So you can open a patcher and look at what's inside, and then you can close it, and that's that. Let me also show one other point that somewhat confuses people. This object is called inlet, and it has an outlet. So you might find that confusing. It represents an inlet to the outside world. So from the point of view of the patch that uses wub, there's 2 inlets and 1 outlet. And so data that comes in the inlet has to be accessible inside the subpatcher so that you can do stuff with it. So this inlet object has an outlet, so that when something goes in wub's inlet, it can come out of that inlet's outlet into your patch to do stuff. And then likewise, after your patch computes its answer, in this case the signal that's coming out of the filter, in order to get it into the rest of the patch, to make that signal come out the outlet of the patcher, you have to go into the inlet of the outlet object. So sorry the terminology is confusing there, but the inlet object has an outlet, and the outlet object has an inlet. I'm going to show you a couple more things about techno tilde. You're going to learn some more shallow knowledge about how this one particular object works, but you're also going to get some deep knowledge out of it. So techno is made to be driven with a signal that says sample by sample, where are we within the sequence? So it's generally it uses what's called a sync signal, which is easy to make with an object called phasor, which makes a signal that climbs up from 0 to 1 at whatever rate that you give. So if you say 0.5, then it'll take 2 seconds. So you've got this sawtooth wave that starts at 0, and over 2 seconds it goes up. And you can see that techno has an outlet that tells you where it is in a position between 0 and 1. And it's going to repeat every so often. So this is something that we're going to learn in a later session about writing sample synchronous processing in MSP, where you do all of the logic of figuring out what's going to happen entirely using signals. And that opens a lot of nice possibilities. But for now, I'm just going to show one of the very simplest things to do, which is to convert this signal on the output of techno that's telling you where you are in the sequence into a bang that comes out every time the sequence repeats. So how do you know when the sequence repeats? Well, normally this signal, this sequence of samples is coming out of the right outlet of techno. Each one is a little bit higher than the previous one. But right at the one sample where it resets, you've got one that's lower than the previous one. So that's what we're going to do. We're going to do a test. So we're going to use a one sample delay so that we can tell the previous one from the current one. And we're going to take that signal and we're going to delay it. And we're going to subtract, sample by sample, the signal from the previous version. So if we put a number tilde in here, what we'll see is that it's almost always a very small amount. But every so often there'll be a sample where this number is not that very small amount. So we're going to ask, sample by sample, is this number greater than 0? And actually, let's ask if this number is less than 0. And almost all of the time, it is not going to be less than 0. So we're going to see a lot of zeros here. But once per repeat, it will be greater than 0. So you can see this signal, it's an impulse train where every time this sawtooth wave resets, after it gets to the maximum and goes back down, that's the one single sample where the current sample is greater than the previous sample. So that's the one time that this less than tilde is going to output 1. And there's an object called edge tilde that converts from signals to bangs. So when there's a 0 to non-zero transition, that's what we need here. A bang comes out. Okay, so we're running this whole patch at signal rate, and we can go as fast as we want, even into extremely high speeds, but exactly once per loop. Just right when it gets to the end, boom, a bang comes out. So if you need to change something, if you want to make something happen differently every time it repeats, then that's how you do it. So I'm going to get rid of these, and I'm going to encapsulate all this. So now that we figure out how to do all this, I'm going to get rid of all the visual displays, and I'm going to take all this logic, and I'm going to just encapsulate it. By the way, there's a shortcut Shift Command E will do encapsulation. So I'm going to call this bang at end of loop. So we're just going to get a bang that comes out every time the thing happens. And I'll leave it to you what you want to do with that bang. Maybe you want to make the pattern change maybe you want to repeat the pattern 4 times, and then after the end of the 4th time, change the pattern. Okay, so our series of web-based patches keeps growing here. So I just put what we did is bang at the end of the loop into this number 4 in the series here. And I give it a load mass so that it defaults to being a 2-second long phrase. And so you see every 2 seconds we're getting a bang here because we get to the end of the loop and it repeats. So that's one thing. Now the next thing I want to show in this number 5 is that although there's this cool JavaScript-based user interface that it graphically will let you set everything for the sequence, you can also do it programmatically. So you can tell it how many steps there are. Normally techno music uses powers of 2, but 7 beats is a good meter as well. So I can have a 7-step sequence here. And you can set the amplitude of each step. Here I'm just going to set them all to 0. So I'm going to use the Uzi object to give me a whole bunch of numbers. Remember, Uzi is 1 origin, so I'm going to subtract 1 because techno numbers is steps with 0 origin, so there's a step 0. So I'm going to set all the amplitudes to 0, and you can see the amplitude is now 0 all the time. And I'm going to set the pitch of step 0 to 50. So when we get to the beginning of the phrase, the pitch goes up to 50, and then it goes back down to 0. Then we'll make the pitch of step 1 be 200, pitch of step 2 be 100. And you can see the techno is sliding between these. And even when the amplitude is 0, that's actually it's just a very low pass filter because we're not making it actually control the amplitude. Maybe we should. So we could go inside WUB and we can make this thing, this second input, we can make it also control the output signal's amplitude. And that's all 0. But let's make step 0's amplitude be 1. And we'll make step 1's amplitude be 0.8. Okay, so you can see I don't want to compose a whole baseline using these message boxes here, but the point is you can. You don't have to do it graphically. You can have messages that get banged at a certain time, or you can make up the messages on your own. You can write a little program that'll generate a baseline, and you do that. It doesn't have to be a baseline, of course. I'm just saying that. But you can set the pitch and amplitude for each step, and you can have however many steps you want. And techno will do that. It also has, if you look at the help patch, it also has not the help patch for comment, the help patch for techno. You can set the pitch trajectory curve. You can set the decay curve. You can set the attack curve. There's all these. You can set the curvature of all these points. So you're specifying specific steps, and then you can set the how much curvature there is from one step to the next. So in other words, anything you can do with the mouse clicking around graphically here, you can also do programmatically by making your max patch send the right messages to the techno object. So I think I'm gonna leave it there for techno. I'm going to show you another kind of subpatcher called a B-patcher. So I'm just going to give a very contrived, made-up example. I'm going to just put some number boxes down, and I'm going to put a +1 in the middle of the sequence. So it's a big patch that all it does is it adds 1 to a number. We'll align them so it looks good. So if the number is 7, 7 plus 1 is 8. Not too thrilling. So we can take this middle part and encapsulate it. By the way, Shift Command E is the key command for encapsulation. And in general, I always recommend giving a name to your subpatcher. So add 1 seems like a good name for that. So this is what we just learned how to make a regular subpatcher. And from the outside world, it just looks like an object that has a certain behavior. And then if you double click it, you can open it up and look inside and see that behavior. Suppose you actually wanted to use some of the graphical objects inside that. Like for example, instead of adding 1, let's make it so that you could add some other number if you wanted to. I'll put a little comment here, number to add. Okay, so we have the feature we can open the patch up and turn it into an add 2 object. And now from the outside world, it's adding 2 to each of our numbers. So that's good. But let's say we wanted to be able to see this number that we're adding. Now, I mean, obviously you could just make 2 objects and put a plus, and you can see them all at the top level patch. But let's just pretend that what it's doing is something more sophisticated than adding 1, but where you still want to be able to see some aspect of the user interface. So turns out, all these objects in Max, if you are in edit mode and you select just to the left of it, you get this yellow triangle that when you click it, it gives you a contextual menu with a bunch of options, including transform patcher to B-patcher. So now that I click that, instead of it being a regular patcher, it's now a B-patcher. So it still works like before. It still has the same behavior. It still has 1 inlet and 1 outlet. But now instead of appearing on the screen like a regular patcher, like this, it appears like a B-patcher, which means that you can see inside it. So even though it's a separate thing, we can see the graphical user interface objects of the bpatcher from the outside patcher. So if I want to set this to 5 and make this into an adding 5 machine, I can. So if we look at the help for bpatcher, you see how this works. You can make the thing inside the patch be in presentation mode, as we learned before, so that what you see is the presentation mode version of it. You can also set the offset of which portion of the subpatcher appears in the outer patch. So by default, you see the upper left-hand corner. So like we see here, if the patch, if we're looking at only a teeny piece of it in the outer patch, then that piece is the upper left-hand corner. But the part that's actually interesting here is number to add. I mean, none of this is that interesting, let's be honest. But there in the inspector, there's an offset. So you can say offset it by 50 pixels horizontally and 100 pixels vertically. And that went in that direction. So let's make it negative 50 pixels and negative 100 pixels. And then, so you can play around with these numbers. Let's say negative 80, negative 90. Okay, so you can imagine getting this right. That 90 seems good, so let's make it negative 90, negative 110. There we go, that looks like what I want it to look like, and we can tighten that up. So you can look at whatever contiguous subrectangle that you want. You can also look at the entire thing by making this big in the enclosing patcher, but that kind of defeats the whole purpose. We wanted to hide as much of the data as possible, so that if we double click, we can look inside and see all this massive complexity of all this incredibly genius programming that we did. But if we're looking at it from the outside, all we see is the user interface. So again, bpatchers, just like a patcher, you encapsulate stuff inside them, but the difference is that you can actually see inside them from the outside. You can still double click, right? You can still double click. There we go. And look inside it. But if you don't want to double click, you can look into the little peephole into the inside that was set with offset and with the size that you sized your bpatcher in the outer patch. Instead of messing around with offset, another kind of thing you can do is you can set the internal patch to presentation mode. So let's see if I can get that right here. So instead of having offset, we'll set these back to 0, 0. So we'll be looking at what's on the inside, and I will double click it. And what I'm going to do is I'm going to put this patch, I'm going to make these two things be in the presentation. And I'm going to go to presentation mode, and I'm going to just move them up into the upper left-hand corner in presentation mode. So there's non-presentation, there's presentation. And I have to do something a little bit tricky. I need to open the inspector window while I have the patch itself selected, so that I can say open in presentation. And it hasn't been opened yet because I haven't saved it yet. So I'm going to save it. Use bpatcher presentation mode. And if I open that, then there you go. So this subpatch is in presentation mode, so I see exactly what I want to see. So by default, it adds 1, but if I set the number to add to, let's make something I can do in my head, to 10, then now it's adding 10. So so it's a bpatcher, and what's inside it is in presentation mode, so that when I look at it through the window of the bpatcher, I see the presentation mode of the inside. And again, I can double click and open it up, and there it is by default in presentation mode, and I can take it out if I want to change how it works. Like for example, maybe I want a load mess so that it will actually show the 1. Because it's a little confusing that this number box says 0, but it's adding 1. So I'll make it always say 1 when it starts. And if I save that and close it and open it again, then I see the 1 is there, just like I meant. So there you go, that's bpatchers. So we've seen how to use subpatchers and bpatchers, and I hope I motivated their use by kind of getting into trouble, just adding more and more stuff into a single big patch. And this idea that's very nice to be able to take a bunch of stuff and kind of wrap it up in a subpatcher, put a box around it, literally and figuratively, and then have just a single conceptual unit that you can think of as its own thing. And if you need to look inside, you can. And if you don't need to look inside, you can just use that thing as a thing, just like you use all the built-in objects. So metaphorically, we can talk about maybe two kinds of situations where you might find yourself wanting to encapsulate something, which I'll call hiding something bad versus hiding something good. So what I mean by something bad is that maybe you've got a part of your patch that's very messy, or it's very confusing, or it's very ugly, and you don't want to take the time to clean it up, or you don't want to take the time to make it less confusing, or maybe it just is confusing. Maybe it's just doing something very complicated and you got it right, and you had to think really hard about that part, and now you're done thinking about it, and you don't want to have to think about it anymore, so you just kind of put a box around it and hope that you never have to look inside again. So that's what I mean by hiding something bad. Taking some part of your program, not that it's bad, not that it doesn't work, not that it's evil, but just that it's something that you'd rather not be looking at when you're thinking about the rest of your program or how to use your program. So that's one kind of way of doing that. That's one good use case for encapsulation. When you have something that's like messy or confusing or whatever, and you just kind of want to like throw the whole mess in the closet and shut the door of the closet and pretend it's not in there. Maybe an opposite extreme to that is what I would call hiding something good in the encapsulation. So you're making some part of the patch, you come up with a really cool wub-based sound, and you're saying, you know what, I'm going to want to be able to use that again. I'm glad I have a thing called wub because I know that that's going to be handy in the future. I know that I'm going to make another copy of it, I'm going to change something in it and do something else with it, or maybe I'm going to make 10 copies of it, I'm going to make some kind of music that uses 10 of them simultaneously. It's that you created something that you believe you're going to have use for in the future. So you've made a subprogram and you've given yourself greater conceptual power by not just having to copy all the contents of that subprogram, but by labeling it as a single thing, you can reuse it as a single thing. So how do you reason about dividing a program into meaningful subparts? Well, it's subtle, it's tricky, it takes taste, it takes experience. I'm going to try to show you some common situations. I'm going to try to lead by example. I'm going to let you see my instincts of when to take something and encapsulate it. I'm going to maybe show you some examples of getting into trouble using these mechanisms. But I want to emphasize that there are, as the metaphor says, there are lots of ways to skin a cat. It's kind of a gross and violent metaphor, but the point is there are multiple solutions to different kinds of problems. And Max is very flexible. Max does not force you to think a certain way. Max does not put its one best idea of how to solve a problem forward as the one and only way to do it. Max lets you solve problems in lots of different ways. And so if you have something, some big idea in your mind and you're trying to figure out how to break it into smaller ideas, I don't want to say that there's only one correct way to do it. I don't want to be dogmatic. I don't want to say that my style of doing things is the only good style. I see that there's lots of people that program Max in lots of different ways, but I want to try to give you some ways of thinking about it, some conceptual resources that will help you stay out of trouble, help you make bigger programs and still be able to keep straight in your mind what's happening. So one of the main ways of staying out of trouble when you're making subpatchers is by naming them well. So by default, when you encapsulate something, if you've got some stuff on your screen and you say encapsulate that, then the name that it comes up with is not a name at all, just P. And it's up to you to type in a name. So I've done that a couple times. I use the name wub. I use the name add1. This is part of my training. That my habit now is anytime I make a patcher, I give it a name and I think what is the most descriptive name for what this subpatcher is doing. So I cannot overemphasize how important it is to name things well. You want to have good program clarity. You want there's this notion of self-documenting code. This idea that your program, if the subpatchers and the variables and everything else that you get to make up names for, if you do a good enough job of making up those names, then maybe you don't even need comments or separate documentation. You can just look at the program and see what everything does. So your program clarity goes up when you name things well. It also is a really good test for yourself as to whether you're making a logical division of your program. So if you've got some big messy thing on your screen and you select a bunch of it and you say encapsulate, and you're like, wow, there's a lot more blank space on my screen. It seems much cleaner. What should I name this part? And if you're sitting there wondering, God, what does that do? It's sort of this, but not really. It's sort of that. If you can't find words to describe what that piece of your program is doing, odds are good that your actual problem is that you're having difficulty thinking clearly about what that piece of the problem is solving. If you can't name the task that the subpatcher does, then you should be suspicious that you don't have a clear idea in your mind of the task that that subpatcher does. So if you can, add one, okay, admittedly, very trivial example, and you don't even need a subpatcher for that, but it's a good name. That is a name that definitely tells you exactly what that subpatch does. So if you encapsulate something, you make a subpatch out of it, and you know exactly what to call that, you've got a descriptive name that clearly and completely describes the behavior of that subpatch. Great, I think you have succeeded in encapsulating. On the other hand, if you can't think of a good name, then maybe you should rethink whether that should have been made as a subpatch at all. So people have different styles of developing software, and with that comes different approaches to encapsulation. So one kind of way of doing it is prototyping. You just you open a blank patch, you start writing, you start adding objects. Eventually, it kind of gets big, and you say, okay, well, all of that stuff that I made, I'm ready to put that in a subpatch. I have a good name for it. I know what its inlets and outlets should be. So I'm sort of building the patch bottom up. I'm prototyping it, and as I go, when I find something that coherently makes sense as its own part of the program, I encapsulate it. I give it a good name. That's good. So that's one way to do it. You can also you can approach encapsulation with a very visual approach. You can just say, okay, I got a big patch. It takes up a lot of the screen. It's getting messy. There's cables crossing over each other. It's kind of tangled. I'm having a hard time understanding what it does. Let me try selecting a bunch of it and saying encapsulate and seeing what it looks like. If I can visually see more clearly what's happening with that patch after I do the encapsulation, then that was probably a good thing. And again, if you can think of a good name for it, then you probably have found a meaningful way of dividing your program into subparts. Another kind of bottom-up approach for
Okay. Hello, Mr. Frank Dreadnought. I didn't expect someone to join my stream. Yeah, I'm writing a comment on a website right now, and I didn't expect somebody would watch. This kind of came out of nowhere. Yeah. Give me a second. I almost got it. Yeah, let's see. Okay, let's continue. Where were we? I was basically watching a tutorial. That's all I did.
Part 1, I'm not even gonna spell this correctly, and that's gonna have an inlet and an outlet. And those are gonna be connected to each other, and then there's gonna be a processing part 2 that happens in parallel with the input, and then those are gonna get combined in some way. And that's gonna have 2 inlets. And so on. Okay, so none of this actually does anything. This is just a bunch of inlets and outlets that have no connection at all. But the idea is that I would sketch out the whole big picture of my program and say, okay, that's the logic. Writ large, that is what my program is supposed to do. And then you can go back in later and fill in the details. So this is a top-down kind of design. You're getting the overall big picture in your mind, and maybe the process of doing that forces you to think more clearly about it. And maybe you revise the big picture before you even implemented any of these pieces. And then once you're happy with the big picture, then you say, okay, now which part am I going to make work first? Okay, let me start with the input part, or whichever part. And then you kind of go back in and fill in the details. Again, like a painter who's made some big broad strokes on the canvas, and then you want to go in and actually make it look like a person's face in this area. So metaphorically, that's one way of doing a sort of top-down design process. Another approach to encapsulation is, this is one that happens to me all the time. With my computer science background, I'm always on the lookout for reusable components. Whenever I solve something, there's a part of my mind that's always saying, how can I make this more general? How can I solve this in a general case? A lot of times that comes from trying to think up a name for something. So you made a thing that is a subpatch, you're trying to think of a name for that subpatch. The name occurs to you, but the name is actually more general. It's a less specific verb than what your patch does, and that makes you think, wow, maybe my patch should do the more fully general thing. And the process of trying to name the patch that you made inspires you to write it in a more general way, a more open-ended way, a way that has less specified in advance and more that can be specified in the future. So that's one way that I program all the time. I'm going along, I'm trying to solve a problem, and I solve a little piece of the problem, and I say, hey, this is a generally reusable component. If I had this as a subpatcher, then I can imagine all kinds of other ways that I could use it. And that's a really good reason to encapsulate something and make it into a subpatcher, because you know that you're gonna have other uses for it. The name that I just came up with for this object makes me realize that there are other ways that somebody could use it. Or another kind of question you could ask yourself is, what if I had 300 of these? So if I make something and I'm inspired to have a bunch of copies of it, then the piece of it that I would want to have copies of is the part that should go in a subpatch. Another kind of sort of hypothetical question that I might ask myself that would inspire me to make a subpatch is, let's suppose there's something it's a problem that I already know how to solve a certain way, you know, going up and down a scale with a counter in a metro. But what if I could replace some piece of that? What if I had a metronome that didn't always count at exactly the right tempo, but that had a little bit of plus or minus? It had a little, you know, it was on average 300 milliseconds, but it's actually somewhere between 250 and 350 milliseconds. So I could imagine a variant of the metro object that's just like the regular metro object, and I could use it just like I would use the regular metro object to play up and down a scale, but it has a slightly different behavior. And so I could imagine, what if I took my scale playing object and I replaced the metro that already exists with this metro that I'm imagining that has this other behavior? So then that metro that has this other behavior, that's a perfect example of something that you might want to make an encapsulated subpatch out of. This lesson is going to explore some of the ways that you can represent data in Max. Last lesson talked about subpatchers and bpatchers, which is a way of encapsulating the logic of your program, the objects that actually process the data. But in this lesson, we're going to talk about how to structure that data itself. Max has several mechanisms for structuring programs. There's a whole topic of computer science called data structures, and there's a sort of a nice pun, the sentence data structures programs. It's structures that are being used as both a plural noun and a verb, meaning that if you organize your data in a certain way, then you can make the program much simpler and more logical, possibly more efficient than other ways of structuring the data. So most interesting programs have data structures, and these mechanisms are they're nice because they give you power in a controlled way, because they force you to represent data in a certain way. It's not just like, here's all these megabytes of program memory, you can put anything that you want in them. The mechanisms I'm going to show you are a structured form of data storage that are optimized to represent data in a certain way. So if the data that you have fits that structure, then that's a good thing. So one of the oldest data structure mechanisms in Max is called preset. It's the preset object. So let's say you've got a program with various objects in it that have a certain state, like these floating point number boxes, and let's put a gain tilde on there. And let's imagine that this is one state that you want to be able to save. You want to be able to go between this state and another state. So there's an object called preset, and it works a little bit funny. You connect the output of it to the objects whose state you want to save. And then if you shift click, then it writes the data. So you can see that there's like somewhat dark gray buttons here, and then this one's like a slightly lighter shade of gray that shows you that there's some data stored in slot 1 of this preset. So we can put some other numbers in there. Let's make them all be 2. And make this higher. And we'll shift click and store that into slot 2. And now if you don't shift click, you just regular click, that takes you back to 1, and that takes you back to 2. Now if you have other objects in your patch that aren't connected to the preset, then they're not affected. When you switch to another preset, what it's saving is those values. It's got some other outlets. It'll tell you which preset you just recalled. So here I just recalled number 2, here I just recalled number 1. This outlet, you can go the other way around. You can say, so this is a sort of opt-in style, where you say, I want to save those objects. I think you can have another preset that if you just say everything except that object, let's try that. Let's put a 1 here, a 2 here, 3 here, a 4 here, and let's try saving that in slot 17 here. And then if we change it, let's make all these numbers be big, and we'll save that in slot 18. So you can see that as I go between 17 and 18, it saved the state of all these number boxes, but not this gain. So the left outlet is a sort of opt-in outlet, and the third outlet is the opt-out outlet. So of course, preset has a help patcher, and you can look at it in general and see what it does. But it saves its data with the patch. So I have a little example here of using the preset object called usePreset. And I'm not going to save that. And so it's got preset 1 with those numbers, and it's got preset 2 with those numbers, and those numbers are actually saved with the patch. By default, you don't have to turn on embed or say, oh no, yes you do, behavior, save preset in patcher. So that is an option that you have to make sure is selected in the inspector here, so that the data will be saved with your patcher. So one way of structuring your programs with a preset, you pick the values that you're going to need to be able to change en masse to make them all take on a new value together, and you either explicitly connect them or you explicitly disconnect the ones that you don't want, and then you can write presets into the preset object and you can save them, and of course you can programmatically recall presets. So you don't have to do it with clicking, you can somehow send it to number 1 or 2 or whatever, for how many presets you saved, and it will recall those presets by loading the values into all these objects. I should say, by the way, that not preset, print. When you go to a preset, it is actually, it's making these number boxes output their new values. So when you go to the preset, they don't just visually display the number, they actually output, in this case, a -111. So if you've got this connected to the frequency of something, I can make all these control the pitch of the oscillators, and the presets could all be different chords, and each preset could be a chord, and you can switch among the chords, etc. So that's the preset object. So preset object, it doesn't really have a name. It doesn't have too much structure, except that your patch already has a structure, and there are already some objects that you're connecting the preset to, and the preset is just kind of, doesn't think about what anything means, it just knows it's connected to certain objects. So when you save a preset, it saves the values of those objects, and when you restore a preset, it sets those objects to that value. Preset object is one of Max's oldest mechanisms for saving the state of a patch. There's a much newer mechanism that comes from Max 7. It's called snapshots. And there's this nice article by Gregory Taylor. You can find on the website. A snapshot is a memory forever that explains snapshots. And I like how it says this here. Simply put, a snapshot is a simple way to store the current state of a VST or audio units plugin or a Max for Live device and save that information with your Max patch. So the preset object is very convenient. It gives you a graphical way of saving data in your patch and restoring it, but it kind of all happens behind the scenes. It all just kind of magically makes some number boxes change, and if that does exactly what you want, then great. But if not, then it's somewhat flexible mechanism. So I'm going to show you now a very, very flexible mechanism, which is to process lists in Max. So we've been using Max lists before. For example, this patch that we looked at that was comparing the two different ways of fading out. We were using the line tilde object to make us to make some amplitude envelopes, and we were using lists. We had a message box that said first send the message 1, which sets the line to output a 1, and then we send a list of two numbers. First is a target, and the second is a duration time to make it to that target. So a list is a linear sequence of data, whether it's numbers or symbols. And actually, you can send a longer list, a line tilde. So if I have a line tilde object, I can put a scope on the outside of it, and we can give it a nice long list, like go to 1 over 2 seconds, then go to 0.5 over 500 milliseconds, then go back to 1 over 300 milliseconds, then go to 0 over 5,000 milliseconds. And boom, it gives us this ramp up and down and back up and then down very slowly. So this is a list of 1, 2, 3, 4, 5, 6, 7, 8 elements. So a max list deep down inside is actually an array, and there's a maximum length of a list that you can set. It defaults to something like 256 or 512 elements, but a lot of max objects can handle longer length lists, so I'll show you in specific how to do that. That's some shallow knowledge that unfortunately you need to take care of. If you're dealing with really long lists, then certain objects that process those lists might not be able to handle lists of a certain length, and you might need to do a little magic to make sure that that works. So one of the things that I do most often with a list is I put it into a message box by sending it into the right inlet. So I'll make this message box nice and big. If I send this list, then it stores that data into that message box. Another thing that you can do with message boxes with lists is you can rearrange, you can use certain elements, or you can construct a list. So you can say, for example, hello, my name is $1, pleased to meet you. And if we print that, then you might be wondering, why is this person so excited about being named $1? But actually it says, hello, my name is 0, pleased to meet you. Because $1 has a special meaning for the message box object. That means whatever came in, let's say an integer, use that instead. So now we have a series of people whose names are integers. That's kind of bizarre. Let's give it a real name like Matt. Hello, my name is Matt, pleased to meet you. And why is it $1? Because you can pass a list of multiple elements into a message box. Instead of saying, hello, my name is $1, I can say $2, my name is $1. And we can say, Matt, hi, exclamation point. So the first element of this list is Matt. The second element is hi, exclamation point. And when I click this, with the patch locked, it says, hi, my name is Matt, pleased to meet you. Whereas if I had something else, like let's say my name was Sally, and my message is go away. So in order to have a single symbol that includes a space, I have to put it in quotes. So this says, go away, my name is Sally, pleased to meet you. So message box, it's the spaces that separate the separate elements of a list. So if I didn't put quotes around it, then the first element of this list is Sally, the second is go, and the third is away. So if I ask for 2, my name is 1, pleased to meet you, then it's going to say go, my name is Sally, pleased to meet you. So to get these two English words into a single symbol so that our list is of length 2, I put them in quotes, as we saw before. So this feature of message boxes is very good for turning one piece of data into perhaps a slightly more complicated list, or maybe if you have a list for extracting certain elements. So like I could make a program that reverses 3-element lists. I could have a message box and it could say like ABC. Whoops, why is it saying append? I just wanted to say ABC. And I could have a message box that says $3, $2, $1, and we can take the output of that and we can plug it into the right inlet of this message box. And what do you know? It resorts it to be CBA, but it only works with exactly 2-element lists. So if I put in a 3-element list, it still has the C in there from before. So it said CMAT, right? And if I put in a long list, 1, 2, 3, 4, 5, 6, 7, then it's going to just throw away all but the first 3. So this is not at all a general way of reversing lists, but just it shows you how to use this mechanism. And unfortunately, it only goes up to 9. So if you say in a message box $10, $1, and you think that you're going to get the 10th element of the list, sorry, you're not. So I say A, B, C, D, E, F, G, H, A, B, C, D, E, F, G, H, I, J, K. And I don't know why I keep wanting me to say append. So if I put that through a message box, I'm not going to get the 10th letter. I'm going to get the first letter and then a 0. So this $1 got replaced with A, and then the 0 that was right next to it got stuck onto the A as part of the same symbol. So you can say things like, it's handy because you can say $1 blah blah blah, and you can send in a message like anything you want, and you can use this mechanism to concatenate symbols together. I'm sure you can find some more useful symbols to concatenate, but that's how it works. So that's why you can't use a 2-digit number with this dollar sign mechanism. It only goes between $1 and $9. But it's really good for just quick and dirty changing things around. So message box's ability to use $1 through $9 to take in input data, possibly an input list, and sort of rearrange it to make an output list. Very handy way to do simple list manipulation in Max. And let me show you kind of a cool feature. So if you control click on the inlet to any object, like I'm trying to do here, like this line object. There we go. If we control click on the input of this line object, it shows you all the messages that the line object can possibly accept. And if you click one of them, then it'll make you a message box that has that message in it, already connected to the object. So if you want to be able to send a pause message, just from right when you looked up to determine that there even is a message named stop, all you have to do is select it in this list, and it'll add a message box. Now, what if there's an argument? So for example, the collection object call that we saw, and we're going to talk about in detail in a moment, has a lot of messages you can send it. One of which is refer, that we talked about recently. And refer takes as its argument a symbol, the one that you're going to refer to. And you notice how it has the square brackets here to show you that it takes that symbol. It's not really the word symbol, it's an argument that's supposed to be a symbol. So if I click that, look at that. It gives me a message box that says refer $1. It knows that I need to specify the symbol that I want to use. And so maybe I will refer it to cold. And if I put that message into the refer object, that's exactly what this is for. So the call is probably going to say, sorry, no such call. Yeah, call, refer is not a call. But if I make this a print object, then we can see that this mechanism is still doing what it's supposed to do. It's taking the word refer, and then after it, it's putting whatever name I've got, and then here's some other name. And if I click on that, then twice, then I see that printed out twice in the Max window. So in other words, this use of the message box with $1 is built into this control click mechanism for selecting a message that you want to be able to send to an object. And if it's an object, if it's a message that itself takes an argument, then what gets inserted is a message box that's ready to set it to whatever you connect into that message box. So message boxes are good for simple rearrangement of lists, taking elements out of input lists and putting them with new data to make output lists. That's all well and good, but obviously 1 through 9, you reach a certain limitation. So it's good for simple tasks. For more complex tasks, you want to use Max's other mechanisms for dealing with lists. So the original mechanism for making lists is called pack. And you give pack as arguments examples of the types of things that you want to have in the list. So for example, if I want a list of 4 integers, then I type 4 integers into pack. And we'll use a message box with its right inlet to see what's coming out. And we can put a bunch of int boxes into the inlet of this pack. And you notice that it's got cold inlets. like most max objects, except for the leftmost inlet. So we can set a bunch of numbers in here, and nothing comes out until I set something in the left. And now we get our list. And if I change the one on the left, it changes. And if I change the cold inlets, nothing happens until the next time that number changes. Or in this case, it doesn't change, but it gets resent. So that's pack. And then the converse is called unpack. And again, you give it arguments of the types of the data that you expect to see. And whereas pack turns a bunch of individual things into a list, unpack does the opposite. It turns a list back into its individual things. So whatever my numbers are, when pack puts them together in a list, unpack takes them apart. So if I give it the list 10, 20, nothing at all comes out of these outlets because this list only has 2 elements. So there is no third element, there is no fourth element, so nothing comes out of it. So these big negative numbers don't change. If I send in a 3-element list, then things only come out the first 3 outlets, and it's not until I send it a 4-element list that something comes out of all 4 outlets. On the other hand, with pack, these numbers are actually default values. So when I say pack 1111, if I don't send anything in these cold inlets, if I just start sending something in the left inlet, then these ones that are the defaults are remembered. And if I overwrite that one, then now only 2 of the ones are remembered, now only 1 of the ones are remembered, etc. So that's pack and unpack. An object that's very similar to pack. So quite often, we used to find ourselves saying, well, if any of these numbers change, I want the output to also change. So we saw how to do that using TBI. So we could make a bunch of TBIs, and we could connect all the bangs to the left and all the I's to the appropriate inlets. And we could have our 4 number boxes going into the 4 inlets to the pack, and like so. So now any number that we change, not just the left one. So these TBIs got rid of made these inlets not be cold, because every time we send something to a cold inlet, we then immediately put a bang in the hot inlet, so something new comes out. So after many years of programmers having to do this to get sort of every inlet hot version of pack, Cycling74 very wisely came up with an object called POC. So just like pack, but with no C. And it says output a list when any element changes. And notice all these inlets are red. They're all hot. And that's how it works. So POC will, anytime it receives any number in any of its inlets, it immediately outputs a new list. So sometimes you want this behavior. For example, if you have a MIDI note that is a list containing a MIDI note number and velocity and a channel, and you do some processing on it and you want to put it back together, you probably want to use PAC because you probably only want one note to be output for every note that comes in. Whereas if you use POC, then you might get multiple notes in a way that you don't want. But on the other hand, sometimes you want, especially on a user interface type situation, if somebody changes something, they usually want to see an immediate result. So that's the kind of situation where you would use POC rather than PAC. To make a list with pack or POC, you need to know in advance what type you want to have. So for example, this POC object uses integers. So if I try to stick a floating point number into it, 1.3, this is an int inlet, so it does me the favor of truncating this floating point number and throwing away the 0.3 part and converting it to an integer. And likewise, if I try to put a symbol into it, in one of these inlets, then symbols, when you convert them to integers, you get the number 0. So POC and PAC are for situations where you know in advance what should be the types of all of the elements of your list. There's another object called join that is more flexible. So let's look at the help patch. So you give join an argument that says how many inlets you want. Let's let this one have 3 inlets. And we'll connect its output to a message box so we can see what's happening. And join lets you have integers or floats or symbols in any position. And it, rather than converting them to the type you said in the first place, it leaves them alone. It gives you the exact data type that it gives you whatever, it leaves the data with whatever type it had originally. So if I say hello, 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 I get a list of 3 symbols. And if I make this be an integer and this be a float, actually let's make this be a float, this be an integer, and this be hello. So I can construct lists where I don't know in advance what are the types of the different elements. Another feature of join is that you get to tell it which inlets are hot with this triggers attribute. So right now, by default, the left inlet is hot and the other inlets are not hot. But if I say at triggers 1, 3, whoops, that's 1. I meant there's 0 origin, so 0, 2. So here's inlet 0 hot, and you can see inlet 2 is now also hot. So this middle inlet is still cold, but the left inlet and the right inlet are hot. And of course, you can make all of them be hot. So this gives you behavior like POC, where every inlet is hot. Let's say you have an unknown list, and you want to be able to add additional elements to it. So you can very easily stick them onto the front or the back of that list using append. So you can say append and many more. And if you put in the message happy birthday, then what we'll get out will be the list happy birthday and many more. And if we send in I don't know, some other message, good morning, then it'll say good morning and many more, sticking whatever you want onto the end of it. And you can change what goes on the end with sending it the message set. So if we set it to a new ending, then now it'll say happy birthday, a new ending, good morning, a new ending. So you can change what gets appended to the end. Likewise, there's this totally analogous object called prepend that does the same thing but onto the front of the list. So it'll say and many more happy birthday, and many more good morning. And I guess we should call this a new beginning. And now it'll say new beginning, happy birthday, a new beginning, good morning. And these work with any length lists up to whatever maximum max has. I don't know why I keep changing my A's into the word append. So this object doesn't know in advance, it doesn't determine in advance how big are the lists that it works with. It'll work with lists up to the maximum. So let me show you some other objects. There's an object route. So we looked already at an object called select that's very similar, where we were using it all the time with a key object so that we could select certain values. So here's the key object. Here's a number box that's holding the ASCII key codes. And so the spacebar is 32, the escape key is 27. So if I select 3227, then what I'm going to get is a bang when I hit the spacebar. Print space and escape. And when I hit the escape key, then it prints a bang. Okay. So what if I put a list into the select object? 32 is the ASCII code for a space character. What do you think's going to come out of that left outlet? Yeah, just a bang. Select's job is just to look at the first element of any list that comes in, and if it matches one of the arguments, then it sends a bang out that outlet. So that's what the route object is good for. Route is exactly like select, except instead of, rather than doing all this, duplicating all this bit by bit, I should have just duplicated the whole thing and just change that to route. So now if I hit space, what goes in here is just the int 32, and other than the 32, there's nothing in here. So the 32 matches the 32 and a bang comes out. But if you send in the list 32 is the ASCII code for space character, then route looks at the beginning of it and says, oh, there's a 32, that matches my left outlet. So everything other than the 32, the whole rest of it, is going to go out that outlet. So if you've got data that's in a list, and the beginning of the list is sort of the destination that that message is addressed to, then you can use the route object to send different data to different parts of your patch. There's also an object called route pass that's just like route. except that it doesn't strip off the number that matched. So if you say route pass 32 to space, the message comes in a list that starts with 32, so that corresponds to this left outlet. But what comes out is the entire list. It doesn't strip off that first character to say, okay, the 32, with route it says, okay, that 32 did its job that caused this message to go out that outlet, so I'm gonna get rid of it, and then you can just look at the rest of the message. But people found themselves having to stick it back on in various situations, which is why the route pass object came to be part of Max. So they're exactly the same. So actually all three of these are very similar, except that with select you always only get a bang out. With route you get the rest of the list except for the part that matched, the first element of the list. And with route pass you get the entire list. It passes the whole list through, but it passes it only to the outlet that matches, obviously. So 27 is the ASCII code for, there's no such character in space, but for the escape key, I suppose. Not sure how the designers of ASCII conceptualized the escape key, but it doesn't really matter. So it's showing you that with route pass, again, well, with all of these, of course, it goes out the correct outlet based on the argument, but you either get a bang or all but the first element of the list or the entire list. Okay, here's another very powerful object for processing lists and symbols. It's called sprintf. It comes from the C language. So it's got print in the middle, and then S at the beginning, and you're printing to a string, S-P-R-I-N-T-F, and F means that it's a formatted string. So format a message of words and numbers. So you give it as an argument, something like, hello, my name is Matt, and if you send it a message, like the message bang, then it outputs what you typed in. So that's pretty boring use of sprintf, like a message box, but we can, sprintf is its own language based on the percent character. If you're a C programmer or C++, then you're probably familiar with this, and you can find that online, but that didn't do much. My describer is Matt. Okay, so %s means a symbol. And then I am %d years old. So if you put in, if you have multiple percent characters, then it takes them in turn. So the first percent thing that it sees is going to be, it's going to refer to the first element of the list that came in, and the second one that it sees is going to refer to the second element that came in. So again, this is a type thing. So S is for symbol, D is for a decimal number, i.e. an integer. So if I send in a fraction, when I was younger, half years mattered more, but in my middle age here, I'm just using a percent sign, but %d just means an integer, so it's truncating. When I say %f, that's for a float. Now it's actually letting it be a float. And if I send it an integer, notice that it added a decimal point there showing that that's actually a floating point number as the 1, 2, 3, 4, 5, 6, 7, 8th element of this list. So if I were to say unpack 1, 2, 3, 4, 5, 6, 7, 8, then here this 8th one would be an actual floating point number that I can do arithmetic on. It's a true number inside that list. Okay, I added 1 to it. Whereas if I said I am %s years old, then it's going to be a string. And if I put in oh, it's too clever. Sprintf object sometimes has strange behavior because after it constructs the string using the low-level C sprintf functionality, the max parser then parses that string. So even though the string had the number 4.5 as a string, the max parser turned that back into a float so that it was an actual float. And again, you can do real arithmetic on it. You can also do these without spaces. So you can have you can use this to construct lists or symbols that have things built into them. So for example, sprintf foo %d dot wave. Let's say you want to save a series of wave files and you want them to be called like foo1, foo2, foo3, foo4, etc. .wave, then you can do it like this. This brings up another point, which is that if you have dozens and dozens of wave files in a folder, and you have one called foo1.wave and another one called foo10.wave, and your operating system gives them to you in alphabetical order, then it's going to kind of mix them. It's going to have 1 first, then 10, then 100, because it'll be in alphabetical order. So you're better off if it said foo001.wave, and that's one of the many things that sprintf can do. You can say %3d, I think. No, you can say %3.d.wave. No, gotta look up the documentation here. Yeah, %.2d. That's how you add leading zeros. That's close. %.3d.wave means make it be minimum of 3-digit number. So even if I put in a 1-digit number, it's giving me these 2 zeros because I asked for a minimum of 3 digits. And of course, if you can have more digits, and it doesn't have to add any zeros in the front. But if you have fewer digits, then it'll do the right thing. So you can look up online documentation for well, first you can read the help patch in Max, but uses the common C language printf functions. For complete documentation, refer to a standard C library reference manual. In other words, the internet. So if you just search sprintf online, you'll see all the different things that you can say. So for example, you can say that your floating point number should only be displayed with 2 decimal points of precision, or you can combine 2 strings together by having 2% s's with no space in between them, or you can convert from numbers. You can interpret numbers as ASCII characters. So 76 is the ASCII code for capital L, etc. So this list of 4 ints can get turned into this nice symbol right here. All right, lastly, I'm going to show you perhaps the most flexible, most powerful way of dealing with lists. There's an object called ZL. Why is it called ZL? It's for Ziccarelli's list object. And you think David Ziccarelli, whom we met earlier as the head of Cycling 74, could just say this is the list object, but it's kind of a historical circumstance. So originally Max didn't have this object, and there were some third-party externals that dealt with lists in different ways. And then finally, David Ziccarelli wrote his own that was way better than all the rest. Plus, it became standard with Max. But so to sort of differentiate his list objects from everybody else's list objects, there's that letter Z there. So that's where that comes from. So the first argument to ZL is a name of a kind of processing that you can do for lists. So basically, every one of these does a totally different thing with lists. So ZL change, if it's the same list as before, then nothing comes out. If a different list comes in, then that comes out. So we saw the change object. Change only works with ints, floats, and symbols. ZL change works with entire lists. So it doesn't matter how many times I send this list. It was only the first time that anything happens. And then if I send another one, then that was a new list. It outputs a 1 to say it was new, and then every other time I output something, it outputs a 0. So there's ZL compare. I want to see if 2 lists are the same. So is ABCD the same as ABC? No. 0 came out, and also it told me the indexes that were not equal. So index 3, they were different. But if it's ABC versus ABC, yes, those are the same. So you can de-interleave a list. So you have a list that has alternating values. You can take all the odd-numbered elements and put them on one outlet, and all the even-numbered ones and put them on another outlet. Another one I use all the time is ZL group. So you say, I want a 4-element list. So I'm going to put in number 1, nothing comes out. Number 2, nothing comes out. Number 3, nothing comes out. We're saving them up. We got the 3. Next one that goes in, boom, there's our list. 1, 2, 3, 4, 5, 6, 7, 8. They come out. If you only put in a couple 9, 10, you can always bang it and get it to output the 9, 10, 11, 12, 13, 14, they come out. So a group is a good way of taking individual elements that are coming one at a time and making a list out of them. You can send a clear to it. And so if you already had a few values, 15, 16, now forget it. Clear. 17, 18, 19, 20.
Depending on your Android, and then we're going to locate the home screen layout, and you're going to see the search bar here. I want you to turn this one off and apply. Going into the customization here, and then we're going to locate the home screen layout. Welcome everyone, I would like to show you how to remove the Google search bar from the home screen of your Google Pixel 6 and 6 Pro. So this is actually still going to be here, but when you tap on it, it will just bring you to settings, okay? So who now be a bit worse or maybe better, it really depends. Over look of your Google Pixel, so just keep that in mind. So you know, if you don't want that to be the case, then okay, you just have to leave the search bar. If you must have the search bar removed, search up for launcher. Nova Launcher is an example. You're going to search up, you know, launcher on Google Play, and you'll have a bunch of other launchers you can download.
If you want to remove or change position, open the Nova Launcher app. Tap on a home screen. That here we select search. Here we select dock below icons, and if you want to in widget
etc. So I'm not gonna read this whole help patch to you, but here's all the ones between F and ME, Mth to RE. So there's whatever, 6 of these separate tabs that are all different. And here's the story about length. So the default maximum list length for ZL objects input and output is 256. And I think that's the default limit for all of Max. You can say, I want you to be able to handle lists of length 1024, and that works fine. So as long as you tell it that you want lists of length 1024 or 2000 or any reasonable number, then it's going to work. So here I'm going to make up 1024 random numbers between 0 and 4, and I'm going to ask it what is the length of that list. And the one on the right, where I used a ZL group that didn't have the first argument to set the list length, it only came up to 256, and it said, hey, that's the biggest list I know how to make, so that's what I'm going to output. Whereas the ZL 1024 group 1024 object actually made us a full 1024 element list. ZL len just tells you the length of a list, but if you don't give it that special argument to set the maximum length, then now it's the ZL len object that's stuck. It says, hey, I received something that's bigger than 256, but I only know how to handle 256 element lists. So there you go. If you're a computer scientist and you think that there's a difference between arrays and linked lists, you're absolutely right. And if you think that a linked list should be able to be as long as necessary until you run out of memory, and you don't need to decide in advance how long that list is, you're absolutely right, which is why it has annoyed me for decades that Max calls these lists, because they're really arrays. How does it work? The object that creates the list allocates a contiguous array of memory to hold all the elements of the list. Each of the elements of the list has to be an int, float, or symbol. Those 3 things are collectively called an atom. And an atom has a type tag that says which of those things it is, int, float, or symbol, and then it has the actual data, the 32 bits of the integer, the 32 bits of the float, or the pointer into the symbol table for the symbol. And if you're an object that's going to output a list, like here, this ZL group object, it's got a certain amount of memory inside it that you have to allocate in advance, just like an array, because it is an array. So this memory is owned by the ZL group object, and when it outputs that list, there's the whole story that I told you a while ago about the depth first search of the tree. So this object, it's in the middle of doing its job, a new stack frame happens, the list comes out the outlet, it goes into the next object, the next, and so on. And all these objects are referring back to memory that is owned by the object that made the list in the first place. So if you have an object that can make a long list, then that memory is owned inside that object, and then it goes through the tree, and then after the last thing does the last thing it's going to do with that list, and we pop all those stack frames and we go back, then this object can pop its stack frame, and the memory that it had the list on can be reclaimed, and so on. So let's use lists to help structure a program. One of the oldest ideas in computer music is what's called the note list, which this goes back to Max Matthews in the early days of computer music. And it's the idea that to make a note, we're going to specify a list of all of the parameters of that note. So we're going to make very simple notes that their parameters are going to be frequency, amplitude, and duration. And we're going to make a simple sine wave synthesizer that takes such lists, and we'll see how all that works. So we'll do that here. So let's make our synth. So we got a cycle, for our sine wave. And it's going to go through a times tilde. This is going to set the amplitude. And we're going to specify it in dBs. So our list is going to have frequency in hertz. Let's make a comment here. Note list colon freq in hertz, amplitude in dB, and duration in milliseconds. Okay, so something is going to make this list of 3 things, and we're going to unpack it as 3 floating point numbers. The frequency is going to control the frequency of the sine wave. The amplitude is going to go to dB to A and control that. You know, I think we're going to be better off if we have some number boxes in here just so that later we can see what this patch is doing. And maybe we even want to look at the output of that. And we will, how are we going to make the duration? We'll make an amplitude envelope. So we'll use another times tilde, and we'll multiply it by our amplitude envelope that we'll get from a line object. And the line object will start at 0. It will go to 1 in very fast 10 milliseconds, and then it'll go back to 0 in the remaining amount of time. And what is the remaining amount of time? It's that third thing minus 10 milliseconds. We're going to use the first 10 milliseconds to go up, and then we'll use all but those 10 milliseconds. I was about to draw a thing from here to here, but I can see that it's going to overlap. So I'm going to make this wider so that that will look nice like that. And just to be safe, let's make sure that the duration can't be negative. So I'll use the clip to say that, in fact, not only do I want to make it not negative, I want to say that the note has to be at least 10 milliseconds long. So the minimum, 20 milliseconds long, 10 to go up and 10 to go back down. So as long as we are, so whatever our number is, we'll subtract 10 from it, and better give clip some floating point arguments that it'll behave in a floating point way. I like that crazy big number that it gave me. So let's see if this works. We'll put those together. So here's an example note list. 440 hertz at negative 6 dBs for 400 milliseconds. Well, hard to see what happened. That looks right. 440 hertz, negative 6 dBs is a 0.5 amplitude. Not sure what happened here, so let's listen to it. David Zuccarelli once said, "There's nothing more boring than watching somebody else patch Max programs together." I think he's got a point. Okay, let's see how this sounds. Yeah, that's right. Let's test our feature. What if we make the duration too small? Let's in fact make it a hugely negative. I should get a very brief 10 milliseconds up and 10 milliseconds down. Yep, so that's good. So let's try another. Let's try a lower one that's louder, that's longer. Okay, so there's our note list controlling this synth. And you can imagine that what I'm going to do, let's save this note list.1. So next thing I'm going to do is I'm going to encapsulate this. Shift Command E. Boom. So there's my synth. And I'm gonna make a few of them. And how am I gonna control them? By the way, Max has unlimited undo and redo. So if you make a mistake, you can just keep saying undo, 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 undo till you get where you want. So here we'll have 2 synths with 2 voices of polyphony. And let's make these longer duration so that I have more time to click. So this one's gonna be long sounds. Okay, so we've got note lists. So instead of having a whole bunch of inlets to this object, we just have a single inlet, and that inlet holds that, through into that inlet is going to come lists that are going to specify all the values of each note. So let's make some simple polyphony. So instead, we'll make this note list 2. Save as notelist.2. So we're going to use a scheduling technique called round robin. So this is something. We'll make this note list 2. So we've got note lists. So instead of having a whole bunch of inlets to this object, we just have a single inlet, and that inlet holds that, through into that inlet is going to come lists that are going to specify all the values of each note. So let's make some simple polyphony. So instead, we'll make this note list 2. Save as notelist.2. So we're going to use a scheduling technique called round robin. So this is something computer scientists know about if you're designing an operating system. Or whatever, then you know about round robin scheduling. Where you basically say, we're gonna have 5 voices of polyphony. So I'm gonna have 5 copies of this synth. And we're gonna take each message that comes in, and we're gonna send them first to the first one. First one's gonna go to the first one, second one's gonna go to the second, third, fourth, fifth, and the 6th one's gonna go back to the first, etc., etc. So every time a new message comes in, we're just gonna send it to the next synth. So we'll have 5 notes playing at a time, and it's gonna work like this. We're gonna have a route object that is going to send lists to one of our 5 synthesizers. They're going to route the note list to these 5. And we're going to have a whole bunch of possible frequencies that we can make. I'll just type in some other notes here. And what we're going to do, every time we receive a note, we're going to have a counter that goes, we want it to count from 1 to 5. So what are the modes again? Loop upwards. 1, 2, 3, 4, 1, 2, 3, 4. Okay, so we want it to be counter 0, 1, 5. So that we'll have this behavior that it'll just keep, every time we bang the counter, it's going to give us the next 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So it's just going to keep going around and around and around. And every time a list comes in, we're going to do two things. We are going to first, we're going to, what are we going to do? I want to stick a new number onto the front of this list. So I think the easiest way to do that is going to be with pack, because I know that these lists are a certain length. So I'm going to say int float, float, float. Oh, and here's the thing I haven't told you about pack, but that's very important. You can send multiple, if you send a list into an inlet of pack, then like the list 106 1000, then it's as if you sent the 1000 to the rightmost inlet and the 6 to the next inlet and the 100 to the next inlet. So that when I say 999, it's got the 100, 0, 1000. So this is one way to stick a single new element onto the front of a list. So and that element is going to be this number 1 through 5. And we're doing that. And so every time a new list comes in, we're going to send a bang to our counter so that we get the next one. So before we connect it, let's just make sure it's working with our message box here. So voice 1 plays that note, voice 2 plays that note, voice 3 plays this note, voice 4 plays that note, voice 5 plays this note, and then it should be back to 1. Okay, so we're just counting up between 1 and 5. So each note goes to the next one of our synths, and then we're going to use the route object to make it go in turn to each of these. So I'm just going to put some buttons on the outputs of route just so we can watch it hitting each one in turn. A little bit ugly, but I think it'll make the point. Okay, so here we go. Voice 5, voice 1. So let's make these durations longer so that they'll overlap. I can only click at a certain speed. Okay, so this is a note list, and this down here is a note list, and this up here is note list with voice number on the front. Okay, so here's our note list. Here's our mechanism that adds a voice number to the front. In fact, since this part is a thing that does a certain thing, I'm going to encapsulate it. I'm going to call this prepend voice number round robin. That's going to tell the person who reads this patch that I'm using a round robin scheduling technique, and we're going to stick the voice number on it. And so every time a list comes in, a new list is going to come out. And then this is going to be the part that actually makes it happen. We could also encapsulate all this and call this our 5 synthesis voices. So that's pretty cool. I'm going to save that. Max actually has a built-in object called cycle, not cycle tilde, the MSP object, but just plain cycle with no tilde, the max object, that does exactly this kind of round robin scheduling. Messages come in the input, and it has an argument that tells it how many outputs to use, and each successive input goes out the next outlet, and it cycles through the outlets in a round robin fashion, just like what we just saw. So max lists are a very powerful and flexible mechanism for combining integers, floats, and symbols into a single data element, a single type that can be sent through Max's black patch cords. You can print lists, you can put them together, you can take them apart, you can ask how long they are, you can do all kinds of processing on them with the ZL objects, like reversing them or interleaving two lists, and they're useful for putting data together in your patch that go together. And the classic example is the note list, where you want to play a note, so you're going to put in that list all the parameters that determine what's going on with that note.